estimate this, you would have to integrate over the period. But and the assumption behind this is that if you integrate over the period length is longer than the mean free path of copper. So it's assuming that you have very smooth variations, but you're still going to have LER. Okay? So what's missing? Clearly what's missing is an analytical closed-form model of effective resistivity as a function of simply size of X, but also of LER. And lastly, what was missing from that previous work was some experimental calibration. They were able to show this, but they were only able to show this on a numerical basis. So we're going to calibrate our model. So I'm going to show the model derivation, describe the model a little bit in more detail, and we'll be able to see exactly how this works. So first we need to describe the LER. So we're going to describe this as opposing sinusoidal walls here. Using this equation. And then we have the model here that we initially that I initially showed with grain boundary scattering and sidewall scattering. And then from lambda, which provides a roughness integral, and that was found here in Japan. And you simply apply the line edge roughness with the effective resistivity model, and you integrate over the period, and you come out with a new model. I know it doesn't happen that fast, but it took a few days. So when you look at the final model, you have simply still the grain boundary reflectivity component, but also along with these sidewall specularity components. So those are still maintained there. So let's talk about the boundary constraints now. Now that we have LER programmed into this, let's talk about the lower bound. So what happens when U is 0? When U is 0, you have a perfect conductor, straight sides. And what happens mathematically is that it collapses down simply into the original equation you found. So that's one check. And also what I wanted to add is that you can see where line edge roughness comes into play. Here you have this added component here, which is going to impact, so line edge roughness is going to be strongly impacted by the sidewall scattering component and also additionally on the overall effective resistivity. Compared to down here to the original equation. Now let's talk about the upper bound of this. What happens? Well, the upper bound is where you actually look at U or LER is equal to the actual line width. And that happens here. So you actually have these pinch-offs. Okay? And effectively that takes it down, it takes it all the way up to infinity. So now you have a physical limit set on a particular chip with a particular process that has an average LER. This is a physical limit on the chip. If you try to manufacture a chip down to a certain LER, you would actually have a lot of opens there. So this is very insightful, and it's good to have this model. So if we talk about the numerical data that was actually published and compare it to the model, you can see it fits reasonably well, but we still want to calibrate this model to some real data. So that's what we did, and I'll talk about that now. So talking about the model calibration, our experimental design was kind of simple. We just fabricated wires with varying effective line widths, and we used a JOL GBX EB lithography tool. It's one of the two in the academic regime in the US, and we used a 2-point probe configuration. We had a contact resistance of roughly around less than 5 ohm. And we used a HP precision semiconductor parameter analyzer to do the resistance measurements. And we used a Carl Zeiss Ultra 60 to do top-down measurements for extracting the LER parameters. And finally, we used the Vico AFM to actually do the step height measurements. So the process flow is really simple. You spin the resist on the silicon dioxide substrate, you pattern the resist with e-beam lithography, and you develop it. You do metal deposition, and by the process of, in our case, evaporation. And there is a seed layer of chrome here, roughly about 5 nanometers, that I used. And then finally, you dissolve the resist in 1165 stripper for about 5 to 10 minutes, and you rinse it and dry the sample. So the final structure looks like this. And when you actually zoom in, you actually see this natural LER that occurred as a result of the overall process. And I can go into more details as to why this occurred, especially with an e-beam lithography tool. But what's important are the data measurements. And what is important is the final overall LER, and that's kind of what the previous two talked about, is we have this overall LER. So here I did some measurements, and these are average numbers. These aren't whole numbers. And so you have the narrowest part, you have the widest part, and then you have this effective line width as a result. These are the drawn dimensions. So obviously with even lithography and forward scattering and back scattering, you have this biasing that occurs. So you can see this is roughly, if I was trying to draw a 300 nanometer line, it would have roughly a 30 nanometer bias added to it. And then pulled out extracted what this undulation was, this net amplitude of LER was. So we first have 14. And then here are the data measurements. Basically, for every effective line width, there is a resistance value that I was able to extract. So you can clearly see that the contact resistance wasn't much of a problem. And simply using the resistance equation here, we can back calculate and pull the effective resistivity out this way. So when we plot this model, we found that a value of P and R equals 0.79. With a fixed value of LER equals 14 nanometers to this line. So now we can say that yes, we not only have found this closed form model that it includes LER, but we have calibrated to real data. May not be the best data, but it's still something that can show exactly what's going on, especially below 100 nanometers. So here's the limit we're talking about, and the limit as line width approaches LER equals 14 nanometers. You can see that if I were to try to use the same process, the assumption is if I try to use the same process and try to manufacture something down to 14 nanometers, I should expect a very low yield for my interconnects. So the next thing I want to show is simply comparing this to a line that is simply with an LER 0. And what the emphasis I want to point at is clearly that if you start looking down into where LER becomes a significant portion of the line width, there's a dramatic difference between the two values there. So now and the last thing what I want to say is, we want to know if we're still within some kind of range, and it seems to agree. There are two authors in our survey for this particular paper that we found that had a p-value of 0. R value of 0.79 seemed kind of high. But again, this is the academic setting, so we could probably expect that. And lastly, let's talk about the projections and what this means for the ITRS. So for the ITRS, we can plot the values in the 2007 version. And what I did was develop an algorithm to back calculate and reverse engineer what the P and R values were of this for a best fit. Granted, you can actually arbitrarily choose whatever P and R values you want, but it still has to fit the data. Okay, so in this case, I want a fit parameter that is 99.99% sure that is fitting to this data. So this is what I found using the parameters from the ITRS, and we found that a P value of 0.95 and R equals 0.4, and assuming LER is 0. We have to assume LER is 0 because there was no LER model before. So if we compare this to the data and to ideal parameters, well, R value seems to be okay, but if we look at the model for the model parameter P, which is specularity, remember I said that if P equals 1, as the electrons encounter the sidewall, they should experience some kind of drift velocity loss, some energy loss. We're clearly seeing that we're seeing more of an elastically scattered event here, higher than what's actually in the data. So that's something to consider as well. So to move on, let's see the impact of LER now, okay? Especially at the end of the road now. What's going to happen? Well, I'm going to clean up the slide a little bit to kind of make it a little easier to read. And here we still have the same parameters, but I'm increasing LER. And it doesn't look like much, but there's more to come. If we increase it to 6 nanometers, there's roughly a 20% increase. And 6 nanometers is something we chose arbitrarily just because of what we found in the literature, and seeing from the previous talk, it seems to be a good number as well. But we can, hopefully we can improve this given the ITRS targets. Then the next thing is, obviously 0.95 and 0.4